Okay, so today we are going to learn how to build recommender systems using Photon ML. And can we have all the presenters stand up? Is Deepak here? I saw Deepak, but okay. So I'm Bichong, and this is Alex, and Paul, Xianxin, and Josh. So this is the outline of today's tutorial. Oops, seem to be messed up. We start with a break, and no. So I'll first give an introduction about like probably 20 to 25 minutes, and Xianxin will talk about the Photon ML library that we are going to learn today. And then we will have a break. I think we probably need a little bit longer break to help everybody to set up the environment correctly. And then we will do the hands-on exercise. So just a preview of what we are going to learn. So we are going to use the Photon ML library, which is implemented in Spark to train a model, and then deploy the model to a simple web interface and look at the recommendation results. And on this result page, you can label or rate a few movies. And then that data get back into the learning algorithm, and it will build a model again, and also different classes of models. And then hopefully see better result. Okay, so and this is the loop that we will go through multiple times, right? Building a model, take a look at the result, rate a few movies, and then data back, right, to the training algorithm, and then do it again. So just a commercial. So today's tutorial will only cover a few recommender algorithms. And if you want to learn more, you can check this book, Statistical Methods for Recommender Systems, written by Deepak and me. Introduction. So what is a recommender system? Right? A recommender system is a system that recommends items to users to optimize for one or a few objectives. I will give many such examples. And nowadays, almost every website is powered by a recommender system. Just take LinkedIn, for example. So if you go to the LinkedIn homepage, you will see on the right-hand side, we recommend the people, right, to user. So here, the items are people, and the objective is, well, we hope that people who receive the recommendation would accept that recommendation and send the invitation, and eventually form a new connection, right, for a given user on LinkedIn. Then below that, there is a LinkedIn ads module, right, in which we, to some extent, also recommend the advertisement to user. And here, items are advertisements, and the objective is to maximize revenue. In the center part, we have a feed of updates from your friends. There are articles shared by your friends and also some other information. And here, each update, right, is an item. And the objective is to maximize users' engagement. And usually, we can measure engagement using, for example, users' interaction. Right? So if a user click, then that's a positive signal. If a user didn't click, then probably there's a lack of engagement. And also notice that there is sponsored update also in the feed, so that the objective is not only one, which is user engagement, but also revenue. So then in this problem, we will be looking at the trade-off between two potential objectives and optimize for both simultaneously. So what is a recommender problem? It is usually can be described in the following process. So we have users who continually visit a website. Right? For each user I who visit the website, we have a set of features that capture whatever we know about a user. and which may include the demographics of the user or the user's past browsing behavior and others. And then an algorithm, a recommendation algorithm, selects from a pool of candidate items a few, usually top K, to recommend to the user. And each item is also captured, right, by a set of features. For example, the keywords, let's say we are recommending articles, right, the keywords in the article or the category of the article. Right. After we make a recommendation, right, recommending item I to user J, we observe, right, user's response. And let's say we use click or not, right, as our response. And this data, right, will later get back, right, into the algorithm that select the item for a user. So the key question, right, is that which item should we select, right, to recommend to a user? And we want to pick the one, right, with the highest click rate, right? So in this case, assume the objective is to maximize clicks. So then we pick the items with the highest click rate. This is called exploration, where we explore the information we already have. Or we may also want to choose an item that gives us the most useful information to improve our current model. Right? Remember that we are also building a model to predict click. And the most useful item that gives us the most amount of information may not be the same, right, as the one that maximizes the click rate. So the second objective is called exploration. Right? So the entire recommended system, right, is basically try to balance this exploration and exploitation. So in this tutorial, we will not cover too much into this exploit aspect. We will focus more on after we collect data, right, how we train a model. And the entire problem is more like matchmaking. Right? We want to match users with items. In order to do a good matchmaking, we need to know our users well. We also need to know our items well and how they interact with each other. So we capture everything that we know by using features. Right? So the first step, right, is to think about what are good features of our users. There are different types of features. So for example, user can declare something about him or herself, right, and put that in the profile. In LinkedIn, right, we have a professional profile for each user. And the information include the title, right, of a user's position and the seniority and the skills, and also the education record, and sometimes people also like endorse other people for certain skills, and also publications. And in addition to user declared information, it's also important to look at the user's behavior. For example, we look at all the users' past activities on the website, right, and try to understand, right, what the user want to look at, and the search queries, right, which represent the user's intent. And in addition to that, right, users are also connect to other entities. Right? For example, user connect to other user. In the case of ranking updates in the feed, right, it is very important, right, to know whether the user, right, who received the recommendation is tightly connected to the sharer, right, who is the user who share a particular update. Right? So if the connection is very tight, then potentially we want to rank that item higher than the update from a other user who do not have a tight connection, right, with this user. And this estimation, right, sometimes maybe we can look at the number of common connections, right, between two users, right, which can be a good indicator. So this connection pattern, right, is another important aspect from the user features. Right? So after we generate and also collect the user features, we also need to look at for items. Right? For the items, what are the things that we can extract from the item to represent that item? Different type of item would have different type of features. So let's take article, for example. So from articles, then we know the author of the article and also potentially the publisher or the sharer, right? The person who shared this article to you. And also the keywords in the title, in the summary, in the full text. And sometimes we may find some named entities, right? For example, people's name mentioned in the article, or organization or location mentioned in the article. And we may also want to extract some topics, right, from the articles. For example, this one probably will be about like data analysis, right? And topics can have two types, right? One is topics defined, right, in a category tree, and then we want to classify, right, an article, right, into one of the nodes or a few nodes in the tree. Another one will be we can also run topic models, right, like latent division allocation, right? So those will be topics identified in an unsupervised manner, right, from the text. In addition to that, we also have users' interaction, right? The number of likes, right, of the article, and also people comments on the article. Right? All those provide information to help us. And also, we can also use neural net, right, to do deep learning and generate latent representation, right, if you really like. Movies. So let me also give a few examples, right, of features for movie. The genre of the movie, right, and also keywords in the title or some description of the movie, and actors and actresses, right. Sometimes that's quite important, right. Some users really like certain actor, and also reviews, ratings, and awards, right. So all those are very useful information, right, that we should capture, right, and generate a feature vector, right, for each of the item. In order to build a good recommender system, after we have features, we apply machine learning. And the approach we take is the following. We first formulate the objective for the recommender system. And then we optimize the objective using machine learning method. And then the whole thing, right, need to be automatic. So this is how we usually form or formulate the objective. So usually we start with long-term objectives, right? So for example, for the case of the news feed, right, we want user to return to the feed. Right? And I think it's important to look at long-term metric. If we look at a very short-term metric, sometimes we may be misled, right? Usually, I think it is very common that you have a new algorithm and you will see performance gain, and over time, it may drop, right? So this is usually called the novelty effect. Right? I think it's important to look at the things in a more long-term manner. However, usually long-term objectives are difficult to attribute to each individual item. Right? When we make a recommendation, we want to evaluate how good each item is. Right? So being able to attribute a value or a utility to each individual item is very important. So that the next, we need to define the optimization objective that is defined on each individual item. So usually those are the proxies, right, for the long-term objective. For example, here we may use click rate, right, as the optimization objective, right? And in the hope that if we make sure that users click more, then they probably will come more often. After defining the optimization objective, then we apply machine learning, right, to learn a model that can predict, right, whether a user is going to click or not. And then we can use that model, right, to rank all the items we have. So the machine learning algorithm will optimize for the optimization objective, and the optimization objective in turn will optimize for the long-term objectives. And it is very important that we need to do a lot of experiment, right, because our assumption may not be correct, and we need to launch a model, deploy to a user, and measure the performance, and then learn from that, and then innovate, and do it again and again. So the whole process, right, need to be automated. The approach we take, right, is to continuously learn from historical data through machine learning and statistical models, and run a lot of experiments. Right? Each experiment helps us to collect more data, and then that go into the model again. And also, we need a very robust infrastructure to support all this automatically. So in the following, I will take a look under the hood of a typical LinkedIn recommender system, show you all the components that we have to support a recommender system. To give such an introduction, so let's probably have a running example, right? So I will be using job recommendation as the running example, right? So user visit LinkedIn, and then we recommend jobs to users. The objective is to maximize job applications from the user. And the model will try to predict the probability that a user I would apply for a job J based on the user features, right, which come from the profile, like industry, skills, positions, companies, education, and also network connection patterns. And also based on the item features, right, like the poster of the job, the company of the job, location, and also important keywords and title and skills in the job. And also all the data about users' past interactions, right, with different type of items. I think not only users' interaction with jobs are useful, right, but also users' interactions potentially with articles may be useful, right? If a user is reading articles about certain skill or about certain company, potentially, right, so the user will be interested in job that require that skill or company or jobs from that company. And also there are many different type of interactions, right? Job application is one, and user can also click without apply, and also save the job and like. Currently we don't have like a job, but you can like articles, and that also indicate, right, your potential job interest. And this is a very high-level overview of all the components that we need to support a recommender system in LinkedIn. And I think it's pretty typical for a very typical architecture for recommender systems in any internet company. So the core is the model machine learning training pipeline. Right? So this is something that we will learn more today. And to train a model, right, we need data. And we need data, and we need to collect data, right, from the system. So then we need a data collection and delivery mechanism, and that is Kafka, which is an open source project that if you want to try, you can also look at that on the internet. After we receive the data, we need to process data to generate features. And the SamesUp is a streaming pipeline that we also open source that can help us to extract features, right, from different type of items and the users. And all the data is delivered to Hadoop. And on Hadoop, we use Pig, Scalding, or Spark, right, to do different kind of data processing. And then the output, right, become like training data feed into the training pipeline. And after we've done the training, right, we need to deploy the model, deploy the coefficients, and also store the features online for the online ranking. So then you need a feature store. Right? So in LinkedIn, we also open source the Vatamo store, which is a key value, distributed key value store that you can also potentially try. And to serve items, right, to efficiently retrieve items, we also need a search index, right, which index all the items, and then we can retrieve the required item very efficiently. And then after we have user features, item features, and also model parameters, we use a ranking and ranking library, right, to generate a score and rank them. And finally, we display the result to a user. And it's very important, right, that we have a experimentation platform, right, that can create different bucket of user, right? Generate different random samples of user, and then test different models around different random samples. So I will go into a few of the boxes. So let's start with feature generation. Right? So we have talked about different type of features, right? User feature, item feature, and activity features. And there are roughly two ways that we can process feature. One is processing feature in a streaming manner, right? When a new data vector comes in, then we process that. Or we can also do batch processing on Hadoop, right? Which is what we call offline processing. Just give one example. So let's say we want to extract skills from a job post. So then we monitor whether there's any new job get into the job database. And whenever there's any change, right, that generate a change event. And the Sensor streaming processing system will be listening to that change event. And for any record that we observe in that change event, we trigger the following DAG of processing units. And this may require some metadata in other systems. And then basically, this skill extractor, right, is also a machine learning algorithm, right, that tries to predict the probability that a job J would require a skill S, right, based on like some human labels. Right? So we also run crowdflower tasks to collect some human labels to be able to give us the ground truth that the skills for each of the job in our training data. And then all the skills also need to be standardized, right, put into taxonomy. And after using this model to predict the jobs, and the result is sent to the Kafka delivery mechanism, right, which help us to deliver data and event, right, to other systems. In this case, we'll deliver the features, the item features, right, in this case, jobs are items, right, item features to a live index updater, and that will ingest the features, right, into the item index. And we also, right, put all the data on Hadoop for further processing and analysis. Now let's look at model training. Right, so we usually start with feature processing, and usually start with raw features. Right? Raw features, for example, are the skill terms, right, that we extract, right, from the job post. And then we usually also need to do some transformation. Right? For example, for numeric features, sometimes you may want to create different buckets, right? Or you can even have a set of if-then-else rules, right, which correspond to a decision tree. Right? Then you can convert the input feature vector, right, into a set of regions, right, in your feature space, which can better model nonlinear behavior. And after you apply all these transformations, right, you generate the final set of feature vectors. So we have user feature vectors and also item feature vectors. And also, some feature vector capture the similarity, right, or how well a user match an item. A few examples like the similarity, like cosine similarity between the user profile and the job post, right, would be just one example. Then we learn the model parameter using a learning library and then basically we are trying to learn the parameters, model parameters, right, for this ranking function. And usually we can classify the parameters, model parameters, into three different types. Right? So the first type is the global parameter vector. And the second type is parameter specific to each individual user, right? So that we can capture that user's behavior more accurately. Also, for every item, right, we may also have a set of parameters specific to that item. For example, the popularity of that item or some like specific behavior of that item. Now, after we apply the training algorithm and generate, right, those model parameters, we need to deploy that, right, from Hadoop to the online system. So in this case, we will be pushing the user parameter to a user feature store. Right? So after training, right, all these parameters also can be think of as features. And then the item feature and the item parameters, right, to the live index updater, and that will ingest all the features into the item index. So now we put everything together, right? So online ranking system works as follows. When a user go on the website, right, the web server will make a call to the ranking service, and the ranking service will retrieve user feature and the user specific model parameters, right, from the user feature store, and all those features, right, are generated, right, from this feature pipeline. Yes, do you have a question? Okay. And the parameters, right, the user-specific parameters, right, are generated from Hadoop and then pushed also to this user feature store. And then we return, right, the user features and parameters to the ranking service. And then the ranking service will pass user features and parameters to the item index. Right? And in the item index, we have features, right, for each of the item. And the index is periodically built on Hadoop, for example, daily or weekly. However, right, there will also be some new item, right, generated after we finish the offline index build. Right? So for those, we will be doing online processing, right, using the Samza, right, which process all the features in a streaming manner and ingest into item index. So after we have user features and item features, and also item parameters, right, also generate offline, pushed to the live index updater. So after we have all this ready, then we compute the ranking function, right, and generate the result. And after we generate the result, it's very important, right, to measure the performance. So we need a system, right, to set up to take like different random samples from user. And it is also sometimes very important to create different user segments. Right? So for example, users in the US, right, may behave quite differently from other places. Right? So then we may also want to break down users by different user attributes and then take random sample, right, from each of these and test model performance. And then we also need to look at the result. Right? After we run the experiment on 2 different random samples, then we compare the performance difference in a large number of different metrics. I think it's also very important not to only look at a single metric, right? Because sometimes you improve one metric, you may drop others. For example, in the feed, sometimes you increase click rate, but then revenue may drop. Right? So it's very important, right, to have a view of all the important metrics and make a decision, right, based on this holistic view. Okay, so this finished the introduction, right? So I think it's a very brief introduction to recommender system. If you want to know more, please check out this book. I'll pass to Xianxin, who will give an introduction to the library that we are going to learn today.
So morning, everyone. So my name is Xianxin. So after the first part of the tutorial is introduction to recommender system given by Bichong. And in the second part, let's look at a very important component in the recommender system, which is the model training part. And we're also going to look at a few models that we're going to build in the next hands-on tutorial. And the library we are going to use today is called Photon ML. So Photon ML is an open-sourced machine learning library that is built on top of Apache Spark in LinkedIn. So before we continue, so let's review a few challenges for build a personalized recommender system, right? A personalized recommender system needs to have a lot of different useful features, but here we want to highlight 2 of them. The first is a good recommender system should be able to adapt the behavior to individual users or items with more data. For example, like a LinkedIn's job website, we want to build quality model for the active job seekers. And for some of the very popular jobs, like software engineer position on LinkedIn, for example, we want to also build a very good model specific to that type of like jobs. And also, sometimes we also need to address some of the different granularities we found in the data. For example, the job applying behavior or pattern may be different from country to country, or even from region to region. For example, maybe a software engineer or data scientist type of position is more popular in the Bay Area, while like the financial analyst is more popular in the New York City area. And in the data, we have different dimensions. We can look at data from the member's perspective, from job, from company. If it's a movie, it could also from a movie's perspective, from a user perspective, from like the stars, like the leading stars perspective, right? So there are different many dimensions. We want to address that. And here we're going to look at a few models that can achieve those desired properties. The first one is a model that everyone is familiar with, that because of the Netflix competition, the matrix factorization proved to be a very useful model that to build a recommender system. So here, we don't need to go into details to explain what is MF, but here we want to pay attention to a few notations that will be used in the remaining of the tutorial. So in this case, we represent MF, the matrix factorization, as a inner product between like the latent factor between the users and, for example, item. And G is a link function. So here we will not restrict ourselves, for example, to a least square type of solution. So by applying a link function, meaning that we are working on like a generalized linear model, their response could be a real response, could be rating, could be binary, could be click or non-click, like or unlike, or could be a count, right? Could be anything. So a G is basically a link function. For example, if the link function G is it corresponds to a logit function, then this becomes we are having a logit regression-based matrix factorization. If the link function is identity function, meaning that it does nothing, then it's a conventional matrix factorization with least square loss function, right? And this one is just expectation of the response, because the thing we care about is we want to predict the response of user on item J. So that's one model. So MF is very excellent in personalization with some not so sparse data, because if we do very sparse data, for example, in ads, click, CTR prediction, the data is too sparse, then MF may not work very well. But if we're working for something like movie recommendation, for example, for Netflix, maybe we have enough ratings, then it may work well. So one of the potential drawback of MF is it doesn't leverage the feature. I mean, in industry, in different companies, we have a lot of carefully handcrafted of features. We want to utilize those features, want to leverage those features in our model. So the second type model we're going to look at is so in the remaining, I will list a few models that we're going to look at. So this is the second one is a generalized linear model. The generalized linear model is same notations. The difference is here we are making a prediction relying on the feature. So Xij is a feature we prepared or engineered for this type of problem. And W is just coefficient vector. In this particular case, if G, for example, again, if G, the link function corresponds to a logit function, this one becomes the logit regression that's I guess everyone uses. And there's a lot of benefits of using GLM. It's interpretable. You can look at the model, understand different features, and you can explore many features with high agility. But there are also some potential drawbacks because, for example, it's not non-trivial to capture some signals from different granularity. For example, we want to build a model that can adapt to active job seekers or popular items. Another type of model is a GAN model. The GAN model is less well known in the recommender system or data mining literature, but it's very well studied in the statistic literature. The only difference between the GAN model, the generalized additive model, and the generalized linear model, the only difference is in the GAN model, we are not only restrict ourselves to a linear combination of features by weight or coefficients. In the GAN model, each of the function here is a smooth function. We will have a smooth function for each feature. And the GAN model is, of course, it's more flexible than a generalized linear model because we no longer restrict ourselves to a linear components in the model. We can dealing with more complicated or even non-parameterized model, but there are also some like potential drawbacks. For example, like potentially it's easier to overfit your model when the data is sparse, and it's very difficult to do model selection within the GAN framework. Right, there are other few like popular models. For example, factorization machine, some models that's gain more and more attention these years, mostly because of we are getting more computation resource than, so factorization machine is a computationally very demanding type of algorithm. But in these days, we have a lot in cluster. We easily can have like hundreds or even thousands of nodes in a computing cluster. So this become no longer a big issue. And in the factorization machine model, the first part is very similar to the generalized linear model. It's features, it's a linear combination of features with coefficients W, right? And the second, the new part that the factorization machine brings to the picture is they can learn the interactions. For example, two-way interactions among the features, and they are applying like low dimension embedding of the latent representation of the features. So that's FM. Another thing is we cannot avoid one type of model we cannot avoid today is deep learning, right? So I just scanned through the KDD's like the schedule. I saw a lot of papers and tutorials, workshops focusing on deep learning, the deep neural network, because recently we have a lot of success applying like deep models in images, in audios, even in natural language processing. And one interesting challenge is how you apply deep neural network in recommender system, how to build a good recommender system with neural network. And later we will address that. So as we see, we list so many different models, like 5 or 6 models already, right? So here's a paradox of choice. So when you are facing with so many different models, and when you're trying to build some recommender system totally from scratch, you have one dynamic in front of you. So basically, which model to choose? Different models have their different relative like benefits, advantages, or drawbacks. Or how do you choose which one is more suited to your data? Which one you want to choose for your particular problem? And the reality is we have, so for all the models I mentioned earlier, they all have like open source like implementation already. But one potential drawbacks is that different models, right, they may be found in different libraries. They may be implementing different language or have different, for example, input-output settings. So if you want to try different models on your data, you need to use the context switch. Might be expensive. For example, if you want to try the logic regression in deep linear, and you realize the deep linear, linear model is not so good, you want to try like the tree models, like a gradient boost tree in like, for example, XGBoost. If you want to try XGBoost, you realize XGBoost is achieve like state-of-the-art performance, but it's difficult to deploy in your production. Then you want to switch, for example, to try different other models. Then you have to constantly switch the context, which sometimes will be very time-consuming. And what is more, for example, if you realize none of the models mentioned above can meet your like requirements, for example, you want to build your own new model, then there might be some more significant effort required for you to build a new model. So here is comes to the point of the Photon ML library. So our design motivation, our goal is we want to provide a unified framework that can harness all the model mentioned above. And within this library, we can experiment different new modeling ideas with high agility. For example, you can try linear regression, it doesn't work. You can try logic regression without too much context switch, and you can try matrix factorization, you can even try other models. And here's the framework we are going to use the next 10 minutes also to discuss. So this framework is called GAM. It stands for Generalized Additive Mixed Effect Model. And later I will explain what this model is, what this framework is. So GAM, there are different ways to explain what is a GAM. So previously, we also gave like a few presentations previously. Sometimes we discuss GAM as a framework. Sometimes we discuss like GAM as like an optimizer if we are facing like the machine learning type person, or sometimes we discuss like GAM as a library if we are facing more like data mining practitioners. So in this talk, we want to combine all of different views of GAM together and give you a like holistic view of what GAM is. So first is GAM as a framework. So as a framework, what is GAM? How can we use GAM? So in a simple word, so here since it's a hands-on tutorial, we will not like deep into details of theoretically or mathematically what game is and all different type of properties of a game. We will not go into that. We just here briefly summarize what is game and to provide you some background later. Then you can, so later you will build a few game models, and then you can get a concept. Okay, what is the model I'm building? Why it makes sense. So in general, games is a framework that unifies and mixes different models into a principled additive model. Here is a simple equation. Maybe this equation might be too abstract. Later we will provide more concrete details, but here it is. So the task, let's say the task is still like we want to predict the response of user I on item J. Right? And here is still the link function, could be a logic regression, could be a square loss, could be a hinge loss, could be different loss functions. And this just as I said, is additive type of model. So we have different components in the model. HF could be a model. We call it effect, but basically it's a model. So this is a framework. Basically, it's a framework that say, okay, this is a framework we're going to handle. It's very still very abstract. It's a model with different additive components. And here is another perspective is what is a game. So once you build a model, how you train a model is actually key. Once you know how to train a model, if you build a model, you don't know how to train, you don't know how to optimize, then it's not a model, right? So again, as an optimizer, it's like give you some example. For example, if we have a model look like this, how are we going to optimize? So in a very high level, what the type of algorithm we're going to use is very simple, very well studied in optimization literature. It's coordinate descent, or sometimes people call it backfitting in statistic literature. It's very simple. So as we see the additive components in this model, here is, then we basically coordinate descent meaning that we are going to optimize each component in turn. So once, for example, when we are trying to optimize the ice component, what we're going to do, we will fix the rest of them. And the rest of them will represent it like a partial score or even a residual. And then the problem we're going to optimize become very simple. We just need to optimize F5, and we don't need to care about other components. So the key about this approach, the key reason, so there's many optimizers out there like LBFGS or Newton method, different optimizers. So the very reason we choose coordinate descent is because gaming is a very generic framework. We have maybe, for some F could be a logic regression model, could be a matrix factorization, could be a combination of matrix factorization and logic regression. Then if we have, it's very difficult to design like a generic optimizer to suit all of them. So a simpler approach, a simpler design choice is we use coordinate descent. In that case, when we optimize each model, we only need to care about this model. So all other models are fixed, and we fix as a partial score and only need to focus on the model at hand. So with this in mind, we move to the third viewpoint of game. So game is a library, because even if we can always publish research papers on different algorithms, but it won't be that useful in industry if you don't provide like a library, like people can directly use in their production system. So game is also provided a library, and again, like we mentioned earlier, so game is built on top of Spark. So later in the tutorial, you will have some hands-on experience building the different machine learning models using Spark. But don't worry, no prior knowledge about Spark is required, because we hide some of the implementation details that involves a lot of Spark. So all you only need to know is it's also a good experience. You can get a rough sense of how Spark works if you haven't worked with Spark before. And in this game model, so what we do is for each of F, it's a building component. So we have different grouping components, for example, available. So for example, we can implement matrix factorization. We implemented general linear model with logic regression, linear regression, Photon regression. And those are building blocks that is already available in game. And the next thing, importantly, next we will, if it's just some well-defined model, then there's no fun, right? We want to build some new models based on what we need, based on the characteristic of the data. So game provides you a way. For example, once we have some building blocks, you can construct a more general model with those building blocks. So let me give some example. For example, we can build, for example, this will be a very important example. So in this particular example, we can build a generalized linear model with matrix factorization. as we mentioned before, like mutual validation is very effective in building personalized recommender system. But one drawback is it doesn't utilize features. We have a lot of good feature engineered like across the years. We don't want to just throw them away, right? We want to still use them in our model, but we still like prefer like MF. For example, we are a big fan of MF. We still want to try MF. So what do we do? So it doesn't matter. So we just have a game model with two components. You can construct a game model like this. You can say, okay, the first part is a logistic regression model, and the second part is a matrix validation model, for example. Just one example. And I will not dig into too much details about other type of model. You can easily imagine we can have matrix validation and, for example, a GAN model, the generalized additive model. We can have like any type of models. So one thing I want to point out here is like a future direction of game. So what we are working on. So it's more like what we're working on. So recently, Google open sourced also a machine learning library, very useful, very powerful, called TensorFlow. So TensorFlow is also like a generic graph-based compute engine. You can also construct different components and make a graph and let TensorFlow to run the model. So one of the model studied in Google's TensorFlow is a model called the wide and deep learning. And this is it's more like a workshop paper published is here. So the fundamental idea is we can also not only combine, for example, a linear model with matrix validation, we can combine like a linear model with a deep learning model. And here's how Google do it. So the first part, for example, is we still have the logistic. So this is still features. Each node corresponds to a feature. We have a linear combination of the features, and here is like the deep neural network. And in deep neural network, for example, the two-layer work, and we will use like the output of the second hidden layer, use the latent representation of the here as the features, as A here, and do a linear combination of it. So this is this type of model is proven to be extremely useful based on the documentation provided by Google Research. And this is something we're also working on. For in a game framework, we're not only able to do the wide and deep learning, we can do even more. For example, we can have other components. For example, we can add like a factorization machine in order to like the two-way interactions between the features. Okay, so that's about game. So because we have limited time in this tutorial, so we cannot explore like all different type of models in this hands-on tutorial. So in this hands-on tutorial, we're going to focus on a specific type of game model. It's called GeoMix. And this type of work, we also like had a research paper like in this year's KDD, and we are going to also present the paper in Wednesday's morning. If you're interested, you can come to our talk. But here's to summarize. So why should we care about GeoMix? So why do we choose GeoMix as like a running example in this hands-on tutorial? Why not MF or why not like logistic regression? So the reason is very simple. So GeoMix now is proven to be one of the it's not just the most useful like model we found in LinkedIn. So by applying like GeoMix model on like the core business of LinkedIn, for example, job recommendation, we achieve like 20 to 30% of lift in terms of job application. This job application is like the key metric, one of the key metric at LinkedIn. This is one of our key source of the revenue, and so we are trying very hard to have a lift in terms of the job application rate. It's similar to other companies, for example, Google or Facebook. They want to optimize like the click-through rates for their ads. For us, we want to optimize the job application rate. All right, we want to encourage more members to apply jobs on LinkedIn website. And not only for jobs homepage, we also have a few other success in LinkedIn's product. We have success in, for example, article recommendation, sponsor update, aka ads, and also other product. For example, people also view this also viewed. So in this tutorial, I want to share some of our like experience, how to build like a quality model, a model that achieve good performance within, for example, a short amount of time. You can, for example, build a GeoMix model like in 10 minutes, and you can see the result using although we don't have the example of job recommendation, but we use movie recommendation. You will see how useful GeoMix is in movie recommendation. So to give us a brief introduction of what the GeoMix is, let's step back a little bit to review what like a generalized linear model is, which is a simplified version of GeoMix. As we saw this before, so to remind you, so this is like the generalized linear model. It's just one single component in the game framework, which is a linear combination. of the features with like the coefficient. So actually the generalized linear model is the first model we tried for like the LinkedIn job recommendation case. So this is the first model we tried. So why we didn't? So why we like later we explored some other model like GeoMix. The reason is very simple. Let me give you a very intuitive example why GLM doesn't work in some cases. So for example, in the feature-based model, this is a model. For example, we have two like LinkedIn members, Alice and Annie. For example, they are sisters. They have very similar background. They are like about the same age. They graduate from the same college. They have the similar majors. Basically, in our model, so a data mining person. So we represent each of our member in terms of a feature vector. And in this particular case, those two members might be represented by very similar member features just because they have very similar background. However, for example, Alice likes to like apply more like startup type of jobs, and Annie's like more stable career, like want to apply more jobs from the big company like Microsoft, just like her like parents. But in this case, if we just apply GLM, there will be a very big problem. So GLM may return very similar set of jobs to both of them just because they share similar features, and that's a problem. So here is a key. So a key to like design get a good recommender system is, as we discussed earlier in this talk, is we need a more fine-grained modeling at different granularities in order to get a better personalized model. For example, here we want to take the past data of Alice and Annie into account and build a more personalized model for them instead of return a similar set of jobs to them. So how are we going to achieve that? So here's where GeoMix comes to play. Probably the same problem, we're still predicting the response of like user on item J. And here's so here's the last equation. So here's what GeoMix looks like mathematically, right? So GeoMix, first of all, is still a game model. It has 3 components. Like I mentioned, so GeoMix is more like a linear version of game. So each component in the GeoMix model is a linear model. In this case, the first one is still like similar to our previous like GLM model. Is just a linear combination of the features. But note the difference here is the global combination of the coefficients. Now in GeoMix model, we can have a per user random effect coefficients and a per item random coefficient for each of our for example, member or jobs. And for example, in this particular case, we will have the user or member specific weight to have a weighted combination of the features. And later I'll give more examples, but intuitively what you want to get from this side is very simple. So GeoMix is a model that can be formulated as GLM model plus a per member model, which is the second part, plus a per item model, which is the third part. So you can easily specify this in game framework. And this is exactly what we're going to cover in the hands-on tutorial. We are going to build like different type of models to address the data with in terms of different granularity. So here is a more explanation of or discussions on what is GeoMix and how GeoMix works for our very key product or running example, the job recommendation. So we still have the global model, which is we call it later the terminology we use is later don't worry about the terminologies because we will see it over and over again during the hands-on tutorial. The global fixed effect model, which is the first model, which is basically aka the logic regression model. It measures similarity between member profile and job profile, as Photon mentioned. So this is just a very traditional logic regression model. We get the features, we get the interaction features, we get all type of features, and we learn logic regression model. And this is a global model. And second model is like a per member random effect model. The difference from a fixed effect model and random effect model. So those, by the way, those terminologies are more from the statistical literature, or more from the biostats. When people say fixed effect model, they mean that there's a model with a global coefficient. When people mention random effect model, then each model will have the coefficient will be specific to each one of the identity you care about. For example, it could be a country, could be a member, could be a job, could be a movie, could be a music, could be an artist, right? And in this per member model, random effect model, what it does is for example, if a member has applied job with the software engineer title, right? What will happen is in the future recommendations, we will boost all the jobs with the software engineer type of job to that particular member based on in her results. And the last component is model is a per job coefficient, the per job random effect model. In this case, is we have a coefficient designed for specific for each of the job. For example, if a job gets applied by some member with a title software engineer, right? And in the future, what will happen is we will boost the job more for so those are LinkedIn members with title software engineer. That's simple. So we call this is just one very specific example of GeoMix applied on job recommendation. So GeoMix model, as we see later in the hands-on tutorial, is not necessarily constrained to only have, for example, per member and per item coefficient components. For example, in ads prediction, we can have a per advertiser model, per member model, per query model, and per keyword model, per title model. So we have different type of random effect models address different dimensions or granularities we found in the data that we found to be useful. So with this model, let's revisit our previous examples and Alice Annie's example. So in this particular example, we no longer apply general linear model, we apply GeoMix instead. In this case, Alice Annie, they will have their own per member coefficient. For example, Alice, we will learn a particular model just for Alice and a model just for Annie. And in that case, they may have different job recommendations, although they are represented by similar feature, because now the model the coefficients for them are different now. We are no longer only relying on a global coefficient. So same idea can be applied to game. What we saw earlier is just GeoMix, but the same idea, the fine-grained modeling can be applied to game. For example, for each of the component now is the only difference now is each f can be a nonlinear. Previously, what we look at is just linear part. So here the f can be, for example, a tree model now. It can be nonlinear, and we have this model can be at the per user level, at per country, or per item level. Okay, so let's conclude our brief background for this hands-on tutorial. So those are the models. We saw different models, and we know that trying different models using different libraries may be the context switch may be very expensive. So we designed a framework, optimizer and library, which is called game that unifies and mixes different type of models into a principled additive model. For example, we have the MF plus GLM model, which is called the regression-based latent factor model. In the literature, in the KDD, just one model we found in the KDD published a couple of years ago, and we can cover some of the more recent models studied in other libraries. For example, TensorFlow, for example, the GLM plus the deep neural network, which is corresponding to the wide and deep learning. So game is just a framework that can provide a way that we can try different type of models. We can explore a wide spectrum of models with very high agility and build our models relatively easily. And the second, we look at the very model that we are going to look at. We are going to study and try in the hands-on tutorial, which is a GeoMix model that give us 20 to 30% of lift, which is one of the biggest lift we've seen. In LinkedIn's core business, the job recommendation example. So we're going to study this example and learn how to build such type of models in 10 minutes or 20 minutes. And GeoMix is simply put it, in the job recommendation case, it's just Geo model with 2 additional components, which is per member and per item. And later, so this is, I think it's the most important message we want to deliver here. Is game, we know game is cool, but how cool it is, we don't know. If I'm just here to advertise game, how cool it is, doesn't really, I don't think it's very important. The important thing is here we will provide it as an open source library, so everyone can try. So after hands-on tutorial, you can try and to feel how if it is usable, how usable it is, whether we want to add more features, whether features in the Photon ML is enough or not. So that's more type of thing we want to deliver here. You can. So game is something we open source it. You can already try at hand, and you can contribute. Also, so because it's open source software, so we also welcome all kinds of contributions back from the community. We want to hear the feedbacks and what your thought about Photon ML. Okay, so without further ado, and I think next we will move down to the. I'm sorry. Yes. Okay. Okay, so I will have a few questions. I can accept a few questions, and next I will have a break. And without further ado, we will move on to the hands-on demo and to tell everyone how to build a GeoMix model, in 10 or 20 minutes. Yes. So here's breaks now. Everyone, you can use the restroom or have coffee. Yeah. We'll come back like in 10 or 15 minutes.